In this video, we're going to do some examples using Gauss's law. You'll come to see that Gauss's law can greatly simplify problems in electrostatics. Usually in order to do so, however, the problem must have some sort of symmetry. So let's start out with a point charge. The previous video we related flux to sun rays of light. Imagine that the point charge is the sun and the electric field are the rays of light. We will choose a surface that can capture those rays in a way that simplifies the integral. The way we can do this is use a sphere. Since all the electric field vectors are pointing radially outward from the center, choosing a sphere will have the vectors pass through the surface in such a way that all of them will be normal to the normal surface vector. This means that the displacement field is constant over the surface. We can pull it out of the integral and evaluate it easily. We can now plug this back into Gauss's law and solve for d. In free space, d is epsilon naught e, so we can substitute this in and solve for e. Note that if this charge was in some sort of dielectric, then the permittivity would just be epsilon. See my video on displacement fields for more info about that. So now that we have the magnitude, we can find the general vector by noting that the electric field will only have a radial component out from the center. Thus, the direction is in the a sub r direction. The next example is a line charge. The total charge in this case is the linear charge density multiplied by the length of the line. So we once again want to make a surface that will allow us to pull the d out of the integral. The surface of choice here is a cylinder. The tops and the bottoms of the cylinder will be perpendicular to the electric field, since the electric field is coming radially from the wire. This means that d dot ds is 0. The sides of the cylinder will always be parallel with the electric field, so d dot ds is simply d ds. Remember that when we look at surfaces, we look at their normal vectors. So we can now pull the d out of the integral and evaluate it, then solve for d. Since the field will only have a radial direction, we know that the unit vector is a sub rho. From here, we can rewrite d and solve for e. Our next example is to find the electric field of a plane surface. We will assume constant charge density, so we can easily find the total Q on the surface. The Gaussian surface will be a box that intercepts the plane. The sides of the box will have d dot ds equal to 0, since the electric field and the normal vector will be perpendicular. The only sides that contribute to the flux are the top and the bottom. Plugging in both sides of Gauss's law and evaluating, then doing a little bit of algebra, we get this. We choose the unit vector a sub z since we know that this is the only direction the electric field will be going. And we substitute for d and solve for e. Our last example is a charged sphere. We will describe what is happening both inside and outside of the sphere. Starting with the inside of the sphere, we choose a Gaussian surface of another sphere with radius little r. The total charge enclosed is the volume integral of the volume charge density. If we assume this is constant, we can pull it out and evaluate the integral easily. Notice that the expression for total charge is in terms of little r. This is because the total charge enclosed is only the charge inside the Gaussian surface. As for the flux integral, we know that d will always be parallel to the surface normal vector. So we can pull d out of the integral and evaluate it. We can now plug this into Gauss's law and solve for d. We once again note that d will only have a radial component, so the direction is in the a sub r direction. We can now move on to outside of the sphere. The approach will be identical, except our Gaussian surface will be a larger sphere. We evaluate Q in much the same manner, except with a notable difference. Now the total charge is in terms of A, not little r. This is because the Gaussian surface is larger than the charged sphere and contains the total charge of the sphere. The flux integral is evaluated in the exact same way. We plug into Gauss's law and solve for d in the same manner as we did before. So now we have an expression that describes the field inside and outside of the sphere. As you can see in this graph, while we are still inside the sphere, the electric field increases linearly as we move outward. This is because as the Gaussian surface gets larger, there is more and more charge contained within it. When we hit the edge of the sphere, however, the electric field drops off as an inverse square law the further we get from the sphere. Pretty interesting. Thanks for watching. Make sure to rate, comment, and subscribe.